So one thing we know is that if we're going to find the slope at a point, then that point has to be there and the slope has to exist from both sides. So we know that continuity is required for differentiability. You cannot take a derivative if the function is not continuous, and this is for every point that you're looking. Now, it's not enough to say that it's continuous for it to be differentiable. We'll discuss that in a second. But suppose you had a problem like this, where you're given f of x equals 3 minus x when x is less than or equal to 1, and it's equal to ax squared plus bx when x is greater than 1. We also know that f prime of x equals negative 1 when x is less than or equal to 1. And if you look up here, this is linear, the slope is negative 1. So it makes sense that the derivative would be negative 1. And then after 1, the slope, f prime of x, is equal to 2ax plus b. So we're supposed to find the values of a and b that makes f of x differentiable for every point. So this is a polynomial and this is a polynomial. They are by themselves differentiable functions. Polynomials are smooth, continuous, no holes, no breaks, everything's fine up until where they meet and after they meet. So we have to make sure that they're okay where they actually meet. So the first step is f of x has to be continuous, which means this piece of the function has to be the same height as this piece of the function where they come together when x equals 1. So I know that 3 minus x has to equal ax squared plus bx when x equals 1. So to figure out the first step of my a and b, I'm going to plug in 1 for x and see what happens. So 3 minus 1 is 2 equals 1 squared is 1 times a plus b times 1 is b. So 2 equals a plus b. That's not enough to solve for either a or b. So the second piece to make something differentiable, not only does it have to be continuous, but the slopes from the left and the right have to match. Remember that the derivative is a limit. So for limits to exist, they have to match from the left and the right. It's the slope formula, so the slope from the left has to match the slope from the right. So this piece of the equation has to equal this piece of the equation when x equals 1. The slope from the left must match the slope from the right. So I know that negative 1 has to equal 2ax plus b when x equals 1. So I'm going to plug 1 in. So I have negative 1 equals 2a plus b. And now I have two equations in two variables, so I can actually solve this. And there are all different ways you can solve this. If you like substitution, elimination, using Cramer's rule with matrices, whatever you want, I'm going to do a simple substitution. So I'm going to take this and I'm going to solve for b. You could just as easily do a. So from this, I know that b equals 2 minus a. I just subtracted a from both sides. Now I'm going to substitute it right there. So I know negative 1 equals 2a, and instead of writing b, I'm going to say plus 2 minus a. So I have negative 1 equals 2a minus a is just 1a plus 2. I can subtract the 2, and a equals negative 3. If I want to figure out what b is, I come back up here, and I know that b is equal to 2 minus a. So that equals 2 minus a negative 3, and b equals 5. So a will be negative 3, and b will equal 5, and that is my answer. Now I mentioned that continuity was a requirement for differentiability, but it's not enough. Imagine you actually have a cusp. It's continuous at this point. Your f would be continuous because I can draw it without picking up my pencil, and that's great. But the slope from the left definitely does not match the slope from the right. So there's no way for me to get a slope of a tangent line at that point. So while continuity is nice, you also have to have a nice smooth curve where the slopes from the left and the right agree.